Most chemical reactions occur by mechanisms that involve two or more elementary reactions. So each elementary step, has its own rate constant and its own activation energy, as diagrammed in the charts from before. An overall process might be multi-steps where the largest energy curve gives us the rate determining step. The slowest step of all gives us the rate determining step. So that overall reaction rate cannot go any faster than the slowest elementary step. This is what's termed as the rate determining step. The overall reaction can only proceed as fast as the slowest step in the multi-step reaction. So we look at the activation energy and find the largest value to determine that slowest step. If it's a multi-step reaction, each one of those elementary reactions has its own rate law, and the rate law is governed by the slowest step. So that rate determining step governs the rate law for the overall reaction. Let's take a look at a first example in which we'll write an equation with the slowest first step. In other words, the diagram would show the activation energy for the first step to be larger than the second step. The rate determining step gives us the overall equation, rate determination. Let's suppose we have a first collision between a molecule of nitrogen dioxide with a second molecule of nitrogen dioxide. It will form an NO3 molecule and an NO molecule. And I'm going to write in parentheses that this is the slow step, indicating that it has the largest activation energy, K1. I'll place the K1 on the arrow to show that its rate constant is coming from that first energy barrier. In a second step proposed mechanism, let's take that molecule of NO3 that was formed above and collide it with a molecule of CO, a second reactant. It would have its own rate constant, I'll call K2. And in this collision, we produce a molecule of NO2 and a molecule of CO2. And I'll put in parentheses that this is the faster of those two steps, represented by a lower activation energy in the second step, K2. I'm proposing a mechanism, a two-step mechanism in which the first step is the slowest and therefore determines the overall rate. The second step occurs much faster due to a lower activation energy. If I sum together the overall equation, canceling any intermediates, I have a molecule of NO2 and a molecule of NO2, one on the left, one on the right. I have a second molecule of NO2, so I could simplify one of them, but it looks like I'll be left overall. NO3, NO3, and that looks like it. So it looks like an overall equation, NO2 plus CO produces NO from the first elementary and carbon dioxide from the second elementary reaction. We get the observed rate law from that first initial step. With this particular pattern, let's label the following words. An intermediate is something that is produced and then immediately used up. NO3 was formed in the first step and then consumed in the second step. NO3 is known as an intermediate. Now, when I look at my overall rate law, it comes from the slowest step. When I look at rate is equal to K, the nitrogen dioxide molecule, NO2, collided with itself in my first proposed elementary reaction. NO2 colliding with a molecule of NO2 gives me a bimolecular elementary reaction showing a second order with respect to NO2. Notice the other reactant, CO, does not even appear in the rate law. Even though it's in the overall equation, it was not part of my first elementary step. The observed rate law for a reaction comes from the slowest elementary step from your proposed mechanism. When I proposed NO2 colliding with a molecule of NO2, I'm proposing a bimolecular rate law with respect to that reactant NO2. Practicing with the decomposition example, let's read this. It says the decomposition of nitrous oxide, N2O, is believed to occur by a two-step mechanism. In the first step, I see that it's slow. In the second step, I see that it's fast. Visually, that's telling me that my first proposed mechanism for that elementary reaction has the higher of the two activation energies. The slowest step determines the rate law. The overall equation is found just by simplifying any intermediates that were formed and then used up. I'm noticing that O was produced in the first elementary and then used in the second elementary reaction. Looks like that's all I'm seeing that can simplify. On the left, I have two molecules of N2O forming, two molecules of nitrogen, and a single oxygen molecule. Two N2Os produces two N2s plus an O2. The overall rate law for the equation above that we just wrote comes from the slowest step. This equation can only occur as fast as the slowest step in our mechanism. Our proposed reaction mechanism would give us an observed rate law, rate is equal to K, times the concentration of N2O to the first order with respect to N2O. This would be a unimolecular elementary reaction. When a single molecule of N2O rearranges itself to produce nitrogen and oxygen, that's coming from that first activation energy, the larger of the two. If it's a single molecule rearranging itself, we called it a unimolecular reaction mechanism. The rate law comes from that slowest first step. Suppose now, in a second example here, we have a mechanism with a fast initial step. In other words, the slow step comes later on in a multi-step process. It's very difficult to derive the rate law for a mechanism in which an intermediate reactant is in the rate determining step. We are not allowed to put intermediates into an overall observed rate law. We have to express intermediates in terms of reactants only. Let me model with this example. If two molecules of NO react with a molecule of Br2 to form 2 units of NOBr, the overall rate law shows rate is equal to K, second order with respect to NO, first order with respect to Br2.